Okay, here's your review solutions for Chapter 5, Part 2, starting with number 4. So let's see, I've got a position function given here. To find the displacement is just, by definition, displacement is equal to the position, change in position. So that's s of 7 minus s of 0. And 7 cubed, oh dear. I suppose you might have been tempted to do this with your calculator. Let's go ahead and say that that's okay. But 7 cubed is 343, isn't it? I think I know that one. 2 times 343. Actually, let me just check. So I'll show you what I'm doing. 2 times 7 cubed minus 15 times 7 squared plus 24 times 7 plus 10. And I'm going to subtract what I get when I plug in 0. Well, that's just 10, right? Minus 10. So that's 119. All right. Total distance traveled. Well, now I got to find turnaround points, right? So let's see. Oh, and by the way, we might need these later. That's 129, and this is 10. Right, that's how I got this. That might save me a little bit of time in a minute. So to find the turnaround points, I'm going to find the velocity here. That's the derivative of this. That's 6t squared minus 30t plus 24. These have a common factor of 6. So let's see. 6 times t squared minus 5t plus 4. And I know, algebra, factoring, whatever, you have to be able to do this. There's a reason you took all those algebra classes. That's really easy to factor. You really shouldn't be busting out the quadratic formula on that. You can, but that's an easy factoring problem. So it looks like we have turnaround points at 1 and 4. So to find the total distance traveled, I need to find the position at 0, the position at 1, the position at 4, the position at 7. And 2 of these I've already got. That's 10, and this is 129, right? So, let's see. I'm just going to copy this here because then I can just plug in 1. Right? 21. You can check my work there. It's 2 minus 15 is negative 13. Yeah, 21 is right. And then plug in 4 into this. So I'll copy that again. So I need to do 4 cubed, and that should really be 4 squared. So that's 16 plus 24 times 4 plus 10, negative 6. So you can see those turnarounds. It goes forward, backward, and then forward again. So from here to here, from 10 to 21, it moves forward 11. From here to here, from 21 to negative 6, it moves backward 27. And then from negative 6 to 129, it moves forward 135. So the total distance traveled is the sum of those. That's 162, 173. Well, that's a little bit of work there. That's how we do it. Okay, intervals on which the function is speeding up and slowing down. I've already got my velocity. So speeding up, slowing down, that's where I have to compare velocity and acceleration. So I know velocity changes sign at 1 and 4, and it goes positive, negative, positive. You can check signs if you want there, but it's an upward opening parabola, so it'd be plus, minus, plus. And let's see, acceleration, the derivative of this, so that's 12t minus 30. If I set that equal to 0, looks like I get t is equal to 2.5. And that's just a straight line that goes from minus to plus. So there you go. So from 0 to 1, they disagree. So that's slowing. And then from 1 to 2.5, these two signs agree. That means it's speeding up in the negative direction. And then from here to here, they disagree. So we're slowing again. And then finally, from 4 to, if you put to 7, because it said to 7 here, but 4 forever more, it's going to speed up. All right, mean value theorem. First of all, this function is continuous on -3, 4, and it's differentiable on -3 to 4. That's true. There's no sharp corners, there's no funny business here. You can take cube roots of negative numbers. Not a problem. So I can make that claim right there. So that means the derivative here, f prime of x, would be, that's the same as x plus 4 to the 1/3. So 1/3 times x plus 4 to the -2/3 times the derivative of what's inside is just 1. So that must equal the average slope, which is f of 4 minus f of -3 over 4 minus -3, somewhere in this interval. Let's see if I can find that. So f of 4, that's the cube root of 8, which is 2. And then f of -3, that's a cube root of 1, which is 1. And then 4 minus -3 is 7. Okay, so the place that I'm looking for is the place where the slope is equal to the exact slope, or the derivative is equal to the average slope. So I got 1/3 x plus 4 to the -2/3 equals 1/7. Algebra. So x plus 4 to the -2/3 is equal to 3/7. And then how do you get rid of that? Well, if you want something to be an exponent to go away, you just raise both sides to the upside down of that. So I need to raise both sides to the -3/2, right? Because then I multiply those and I get 1. That will cancel those out. So x is equal to 3/7 to the -3/2 minus 4. There's different ways you can mess with that. You could say that it's 7/3 to the +3/2 if you want to, but that's okay to write it like that. Actually, it's kind of not okay, I guess, to write it like that, because we don't want to use negative exponents and have fractions that way, so that negative exponent flips that over, so I think maybe it's better to write it like this. But if you have that, that's also correct. All right, number 6. At what x values does, so this is a graph of the derivative, right? So where does at what x values does this function have a maximum? Well, it has maximums where the derivative, where it goes from increasing to decreasing. So that's from positive to negative. So there's a maximum, and there's a maximum, where the derivative goes positive to negative. So that's at, let's see, -2 and 2. And if we wanted to justify, that's because f prime goes positive to negative. Where does it have a minimum? At 0, because f prime goes negative to positive. On what intervals is f of x increasing and decreasing? Well, it's broken up by these, right? Here it's increasing from negative infinity to negative 2, and from 0 to 2. And then it's decreasing from negative 2 to 0, and from 2 to infinity. Where does it have inflection points? Well, it looks like it's around 1-ish. I don't know, maybe a little bit less than that. I'm going to say, reading from the graph, it looks like it has inflection points where the slope of the derivative changes sign. The slope of the derivative is the second derivative, and we need that to change sign. So the slope of this is negative, and then positive and negative. And the slope of the derivative is the second derivative. So we go concave down, up, down. So inflection points at approximately negative 1 and 1. And then we just said that. So it's concave up from negative 1 to 1, roughly, and concave down everywhere else, from negative infinity to negative 1, and from 1 to infinity. That is all the information you can read out of one of those graphs. So we did that all in number 2, right? Now we're just given the graph. All right, that is important stuff to be able to understand. Let me tell you what. All right, and then this looks College Board free response kind of thing here. Let's see what we have. Consider a differentiable function, f, having domain all positive real numbers, and for which it is known that this is the derivative for x greater than 0. So the domain's all positive real numbers, and there's its derivative. Find the x-coordinate of the critical point of f, and determine whether the point's a relative maximum, a relative minimum, or neither, and justify your answer. Well, critical point happens when the derivative is equal to 0, or undefined. So let's see, f prime of x is equal to, I'm going to write this like 4 minus x over x cubed. Now, it's undefined at 0, but 0 is not part of the domain, right? The domain is only all positive real numbers. So we've got a critical point at x equals 4. If I make a sign chart of the derivative, it looks like that's going to be positive on both sides. So it goes from, if I plug in like 3, for example, it goes positive to negative. So there is, x equals 4 is a positive negative, a maximum, and we justify by interpreting the sign chart because f prime goes from positive to negative. B. Find all intervals on which the graph of f is concave down. All right, for that we need the second derivative. You can do it in this form, or you could go back and do the product rule with this. I think I'm going to go ahead and use this. Let's see how that looks. So low d high minus high d low. Oh, hold on. I'm going to run up and turn the announcers off. Hold on. I'm coming back. All right, let's see if we can finish this before the bell. Okay, so low d high minus high d low over low low. So inflection points, I'm looking for places where this is equal to 0 or undefined, but that's not part of the domain. That's only at 0, so I don't have to worry about that. So I need to set that top equal to 0, and I need to simplify that. So I have minus 4, that's minus 12x squared, and then plus 3x cubed. So that's 2x cubed minus 12x squared. Doing some factoring. Looks like my critical point is at x equals 6, doesn't it? So I think I didn't make any mistakes there. So, not my critical point, sorry, my inflection point. So the second derivative at 6 is equal to 0. So I'm going to make a sign chart for the second derivative and check both sides. This right here is just a simplified version of the top of this. The bottom of this, always positive. The top of this is equal to this. That part, always positive. So it looks like it changes from negative to positive at 6. And they want to know all intervals where f is concave down. So it looks like concave down on the interval from 0 to 6. Don't include that because it's x greater than 0, domain's all positive, because f prime of x is negative on that interval. All right. C. Given that f of 2 is equal to 3, write the equation for the tangent line to f of x at x equals 2. So I've got the point 2 comma 3, and I know the derivative. I have it right here, right? So f prime of 2 is equal to, plugging 2 into this, 4 minus 2 over 2 cubed. So equation for the tangent line is y, let me do it in point slope, y minus 3 is equal to 1/4 times x minus 2. There's my tangent line. Use the tangent line to approximate the value of f of 2.1. So f of 2.1 is approximately equal to what I get when I plug 2.1 in here. So I'm going to move the 3 to the other side. 3 plus 1/4 times 2.1 minus 2. And that's, let's see, that's 1/10. So 1/10 is 1/4 is 1/40th. So 3 and 1/40th. You could write it like that, or 121 over 40, or however you want to write that. But it's a no calculator problem. All right. Does the tangent line overestimate or underestimate the actual value of f of 2.1? Well, this is a second derivative test problem. I know that at x equals 2, that f is, going back to part B, it's concave down. So that means my tangent line here, if you got a function that's concave down, the tangent line will be above the function. So I'm going to say since f double prime of 2 is positive, the tangent line will overestimate. Right? If my function's concave down, the tangent line is up here. That means this estimate is a little bit too high. Tangent line overestimates. That's an application of the second derivative test. Now, I'm not going to make it by the bell. Dang it. A point moves along the curve y equals f prime of x. So it moves along the curve y equals this. If dx dt equals 2, how fast is the point moving away from the origin when it's at the point, when it's at 2 comma 1/2? Okay, so I've got it. Now I'm interpreting this 4 minus x over x cubed as a curve. I've got a point moving along the curve, y equals f prime of x. If dx dt, as soon as you see that dt, like boom, this is a related rates problem here. So I need to take the derivative of this with respect to time. So dy dt is equal to low d high is negative dx dt minus high d low is 3x squared dx dt all over low. So we want to, how fast is the point moving away from the origin when it is at 2, 1/2? And I also know that dx dt is equal to 2. Okay, so there's a couple things to think about here. I need to find dy dt, right? I know what dx dt is. Dx dt is 2, and what that means is that's how fast it's going. That's the rate of change dx dt in the horizontal direction. And then if I can find dy dt, then that would be the upward, right? That's the upward part. And then if I find this, that is the Pythagorean, that's like the Pythagorean theorem on those. That's the actual speed that it's moving. But hold on, let me reconsider this for 1 second. We want to know not how fast is it going in general, but how fast is it moving away from the origin. And I think that might be slightly different than this. So let me grab a piece of scrap paper because I don't have enough room here. Hold on 1 second. So I think this is one of these problems like what we saw in some section 5.5. So we have a curve we have this, and we also have the point 2, 1/2. I'm sorry, we also have the origin, right? So we would like to know what is, how fast is it moving away? So the distance between any point on this and the origin, any point on this is of the form x, 4 minus x over x cubed. And the other point we're interested in is the origin, so that's nice. So the distance between the origin and this point is distance formula. So it's x minus 0 squared plus y minus 0 squared. That's the distance between this point and the origin. And we want to know how that distance is changing when dx dt is equal to 2. So let's see if we can do this. So taking the derivative of this equation with respect to time, we have dd dt is equal to, I guess I better simplify this first, huh? Let me do a little bit of simplifying here, and we'll rewrite it with a 1/2 exponent. So I've got x squared here, and then here I've got 16 minus 8x plus x squared all over x to the 6th. And if I wanted to get common denominator. Is that going to do me any good? It might. Then I could simplify this, multiply the top and the bottom of this by x to the fourth, and get x to the fourth plus x squared minus 8x plus 16. Just change the order of those so my exponents are going down, all over x to the sixth. Well, x to the sixth, the square root of that would be an x cubed on the bottom, so I can do that if I want to. Alright, well, there's a simplified version of that. Let's see what it does when we take the derivative. Okay, so the derivative of this, and remember we're taking the derivative with respect to time, so when I take the derivative of an x, a dx dt is going to pop out. So I get 1/2, this is chain rule, right? Not chain rule, sorry, product rule. So 1/2 times this thing, x to the fourth, plus x squared minus 8x plus 16 to the negative 1/2, right? Times, that's the derivative of the first, times, now I need to multiply by the derivative of what's inside. The derivative of x to the fourth is 4x cubed dx dt plus 2x dx dt minus 8 dx dt. Okay, that's the derivative of the first times the second plus the first times the derivative of the second. And I'm taking the derivative of something with an x in it here, so don't forget that another dx dt is going to pop out there. Okay, so I think we actually have all of the information that we need here. So dd dt, which is the distance, that's the rate of change of the distance between our point here on this function and the origin, right? That's the rate that that's changing at. And now we want to do that when it's at the point 2, 1/2, and when dx dt is equal to, was it 2? To 2. So that means every place where I see an x and every place where I see a dx dt, they're both 2. So everything has to become a 2. All right, so 1/2 times 2 to the fourth plus 2 squared minus 8 times 2. So that's going to clean up kind of nice. And then here, 4 times 2 cubed, times another 2, plus 2 times 2 times 2, minus 8 times 2, times 2 to the negative 3 is really 1/8. Alright, so there's that whole mess. And then this, I already did that, didn't I? That's this. That's, those cancel, so that's 20. That's this thing, to the 1/2. Minus, no, sorry, that's times, isn't it? Times negative 3x to the negative 4. That's negative 3 over 16 times dx dt. Okay. And here, let's see. So this is 1/2 times 20 to the negative 1/2 times, let's see, 64 minus 8 is 56 times 1/8. Okay, more simplifying to do there, but let me keep going here. So plus 20 to the 1/2, that's the square root of 20, and then times negative 3 over 8. That's 7. So I've got 7 over 2 square roots of 20 minus 3 square roots of 20 over 8. And hey, while we're at it, let's just get a common denominator because this is so fun. So I'm going to go ahead and multiply the top and bottom of this by the square root of 20. So 7 square roots of 20 over 40 minus, and then if 40 is my common denominator, I need to multiply the top and bottom of this by 5. So that means that looks like I've got negative 8 square roots of 20 all over 40, and the square root of 20 is 2 square roots of 5. So what does that give us? I've got a square root of 5, and then woo! That was fun. Kind of simplified a lot, didn't it? Listen, I made up that problem, and I did not intend it to be that crazy and messy. But it's good practice. It's a good little reminder of related rates when you see that dt. Related rates can pop up here and there in problems when you don't expect it. Not saying that it necessarily will on this test, but they can always come up, and it always surprises us when it does. So apologies for that. There you go. Good practice.